Hello, everyone, and welcome to Steel for Lunch. If we haven't met already, I'm AJ Daras. I work in the Steel Center, and we're happy to host today's presentation on the design of moment connections using bearing effects by Mojgan Yarobshahi. Did I say that right?
Yeah.
Yeah, okay, Yarobshahi. Sorry about that. And I'll hand over to her in just a few seconds after a couple of housekeeping items. So first, you'll notice you are muted on entry. This is for everyone's listening pleasure and to reduce feedback. But if you have any questions, feel free to click the raise hand feature, send the chat, or unmute your microphone at the end for questions. We will try to end on time at 1 p.m., though we may go a bit longer to answer a few questions. But if you have to leave early, we understand. And for those of you who are new to the Steel Center, we're actually supported by a large group of industry members. So we want to take a moment there to thank all of them for their support. And I would also like to celebrate with everyone here the 5th anniversary of the Steel Center. So I think we've prepared like a short video about that. But it'd be nice to show everyone. Yeah, awesome. So happy 5th to the Steel Center, and many more to come. So I'm just going to introduce our presenter here today. So our presenter is Mojgan Yarobshahi. She's a postdoc fellow here at the Steel Center, and she's worked in both academia and industry for about 13 years. In academia, her research focuses on steel structures, specifically steel thin walled structures and hollow structural section connections. And in industry, she worked in design consulting, steel manufacturing, and she's also experienced in design and construction of steel and concrete and hybrid structures. She graduated from the Tehran Polytechnic University with a PhD, and she's a PhD with in both BC and Alberta. So with that, I'm going to hand over to Mojgan, our presenter today. So you should be able to share your screen.
Share my screen first.
Okay,
yeah. So, do you have my screen now? Yeah. Hello, everyone. Mojgan Yarobshahi here from Steel Center. I'm happy to have all of you here joining my presentation today. It's at the time that the COVID-19 pandemic actually makes everyone just feel more like isolated. We're all practicing social distancing. So, but I'm very happy that we've got such a virtual communication tools that we keep us stay connected and keep on our social and also professional and mental development. Today, in my presentation, I'm going to talk about the structural design of moment connections, accounting for bearing effect in Vierendeel trusses. A Verendeel bridge is a bridge employing a Vierendeel truss. This bridge is named after Arthur Vierendeel. In this, Arthur Verendeel was a career both as an engineer and also a university professor. He started his career as a civil engineer in a consultant engineering company, and then after he became director for Ministry of Public Works in West Flanders in Belgium. And then he got a position as a university professor. And the idea of a Verendeel bridge, actually eliminating the diagonal elements from a traditional bridge, came to him in 1895. And he built a bridge with such truss pattern, as you will see, compared to the traditional truss patterns. The diagonal member are eliminated. So he kind of built such bridge, and in 1897, in a world fair at Brussels, he loaded such bridge, and to show that his calculation matches the way that he calculated matches how the bridge sustained the loads. And we all know that at that time, actually, there were no like finite element software, and he did some like prepare some using some analytical methods, some closed form solution, to show that his calculation actually matches the load that the bridge sustained. After that, this type of bridge was very became very popular all over the world, and all over the world in Europe and North America. These type of truss pattern has been implemented in the construction of bridges. We have the bridges, Ocero de Pro Bridge in Spain. We have the Monke-Worms railway bridge in UK, and so in all over the and we have the bridges in France and also again Germany. They have used such a truss pattern in the construction of bridge structures. The main reason that they have this truss pattern has become very popular is because of the nice and attractive outlook that it provides compared to the traditional form of trusses. And also this form of truss, Vierendeel trusses, has also been implemented in the building construction as well, because as I mentioned, they are very architecturally attractive because they provide such wide opening. See, if you want to compare these two figures, if we had such like the traditional trusses, we wouldn't be able to have such nice and wide windows. So for architectures, they are very popular and attractive. And also these type of trusses, which also can be used in the ceiling, and they call Verendeel girder, are very popular because it provides such easy access and such wide opening to run through all the mechanical piping and plumbing. And also, if you look at this industrial building, they was able to run a pathway through the ceiling of the buildings. So. And they have been widely used in industrial buildings as well. See these girders, these open web girders have been used for runway beams for a crane. And these are for the bridges, it's a crane. And then they have also been used for the crane bridge as well. And also in building, they have been widely used. These open web girder, these Verendeel girders, they have been widely used in building constructions as well. In addition to the nice outlook and that this type of truss pattern provide is that because of absence of these diagonal elements, in terms of fabrication, actually they are very cost effective because they come with a lot less fabrication detail compared to the traditional truss pattern. So and there will be less fabrication detail and less complication. And actually these days, due to aesthetic considerations and also structural efficiency, hollow structural sections have been very popular in construction of such truss systems. So they are mainly used in construction of truss systems. And here is a schematic view of a truss, a Vierendeel truss. See, these are we have horizontal elements that they are called chord elements, and we have vertical elements, and they are called vertical webs or branch. And when we all hear the term of truss, all comes to our mind is the simplest structural element, right? They only have axial forces, and the connection are pimping connection, simply supported. So the simplest structural element that we deal. But it is not the case in Vierendeel Truss. Actually, due to eliminating these diagonal elements, there will be substantial moment in the truss elements. There will be large bending moment in the branches and also in the chords as well. And these connections are not pimping connection. They are actually moment connection. But the thing that makes the design of such connection a little bit like challenging is that these moment connections are not actually like typical moment connections because they are not fully rigid connections, and they are called like semi-rigid connections. So this is what makes the design of such connections a little bit more like complicated compared to typical moment connections that we normally deal with. And these subjects, I don't think that they are covered in like undergraduate curriculum. At least at the time that I was doing my undergrad, I never was taught about this. And but one of the good reference that actually provides a design guideline to deal with the design of such connections is AISC 360 Chapter K, which covers all the design recommendations and all basically we need to consider in design of such connections. And also there is another reference as well, CI D3, that covers the design recommendation. Actually, when we deal with design of such semi-rigid connection, then actually when we implement the HSS profile. So As I mentioned, these connections are not fully rigid connections. Okay, they are semi-rigid, but the flexural strength and rigidity of the connection depends to the connection geometrical and material properties. Okay, so there might be some situation that they become fully rigid connections. So let's say that if we have very strong chord, then we will face a fully rigid connection. But in all other cases, actually, they behave like semi-rigid connections. So in order to kind of classify and find in method to determine if they are like semi-rigid or if they are fully rigid. So AISC actually provides defines two parameter, beta, which is the branch width to chord width ratio. And then it defines actually chord wall slenderness to gamma, which is defined as B over T ratio, which is the chord width to chord thickness. So as a branch to chord width ratio, which is beta, decreases, and the chord wall slenderness value increases, the rigidity of the connection decreases. So, we will have a fully rigid connection in case if beta is equal to 1 and B over T ratio is very low, then we will have like a fully rigid connection. In other cases, the connections are semi-rigid connections. So in order to design of the connection, I mean the chord elements and also the branch elements, in order to size them actually. So there are different modes of failures. And it depends again to the connection characteristics and the properties. So there are 5 modes of failure associated with the design of such connections. The first mode of failure is chord face plastification, and as it is displayed in this figure, figure number A. So this is how it would look like if the chord face actually undergoes plasticity. And the other modes of failure are punching shear, again at chord, and also local yielding in the branch. That is, these are another modes of failure. And another mode of failure is chord side wall local yielding. See if there will be some plasticity happens at the chord side walls. And another mode of failure is chord shear failure. So, and as I mentioned, that which mode of failure governs this design, it all depends to the connection, geometrical and material properties. And AISC 360 has provided some formula. These formula actually have been presented in AISC 360 2010, and in 2016 actually they have changed the structure of that chapter a little bit. So, and I didn't cover those because it's out of the scope of this presentation, but these are the formula that could be used for design of the connection as well, the connection elements, I mean the chord and the branch elements, how to size the thickness, the width. Yeah, these are the design recommendation. And as you see, AISC define a width effective width, which is kind of a parameter that shows how rigid is the connection. So if the connection actually is semi-rigid, which is the case in most of the situation, the stress distribution at branch perimeter is not uniform. Actually, there will be a non-uniform stress distribution at the branch element. And B effective or effective width is defined to kind of represent what portion of the branch element is effective in transferring the load, because when it is a semi-rigid, not all the width is effective in transferring the axial stresses. So these are all the design requirements that we needed to know to design the chord and branch element itself. But for design of the weld, there are two design philosophies in AISC actually, and in also the CI as well. So the first design philosophy assumed that the entire branch perimeter reaches to yielding. This design philosophy, this design method actually is very conservative, because as I mentioned, it is not the case in all of the situation, and not in all the situation actually the entire branch would yield. And there is another design philosophy which is called fit to purpose. So this design method actually uses the underlying assumption that is available for to show the non-uniformity of the stresses around the branch perimeter. So if we want to just run the numbers using the first design philosophy, let's say if we go with the AISC 360, so the weld that we require, the weld thickness that we require to design this connection would be 1.43 times of the branch thickness. So actually in a experimental report done by McFadden and Professor Jeffrey Pecker in University of Toronto, they have run the numbers based on this design philosophy for based on different design codes, and these are the weld thickness that they needed actually if we wanted to design such connection based on this design method. And but as I mentioned, that design method is very conservative, it's too conservative, and this is why that in AISC Chapter K, actually they have adopted the second method, which is designed for purpose. and they have used that be effective concept, and they have actually kind of developed the design requirements based on that weld effective properties. But yeah, then at this, based on the second approach, it is assumed that the fracture actually happens in the weld, not the entire branch would yield. So the failure would happen in the weld, not in the branch. So, and these are the design requirements, design formula presented by AISC to design the weld based on the second approach, which is a design fit to purpose design method. So, and these are so basically, in order to calculate the bending capacity of the welded connection, we calculate the section modulus of the weld, and then we multiply it by the weld strength, and then we calculate the capacity of the welded connection for both in plane bending moment and out of plane bending moment. But 12 actually HSST moment connection tests were conducted at the University of Toronto, and it was found that so the two these are the test setup for 12 HSS connection with different geometrical properties, both match connection with the beta between 0.85 and 1, and a step connection with beta between 0.25 and 0.85. So, and these are the the geometrical properties of all the connections that were covered in the experimental program, and both all the connection capacity also were calculated to make sure that these are all the the mode of failure which was governing each connection. So, for example, for the first connection, which with the beta 0.25 and 2 gamma 34, so the governing mode of failure for connection design was chord wall plastification. And then, yeah, all these mode of failures were identified for all 12 connections, and also the weld capacity also were calculated based on the current design requirements of the AISC 360, and it was make sure that the fracture in the weld happens before failure in the connection. If you look at this column, you will see all these ratios are smaller than 1, which means that the fracture in the weld prevail the design of the connection. So, and then a comparison was done between the actual strength of the connection, which were obtained from the experimental programs, with those value calculated based on the current design formula of the AISC. And if you take a look at this column, you will see that kind of the current design formula in AISC is very conservative, and you will see that the ratio of the actual strength of the connection are almost more than 2 times of those value actually calculated by current formula in the AISC. So in order to kind of figure out, and so it was found that, okay, AISC is over conservative. So in a research work, we decided to kind of provide some design recommendation to kind of provide that could calculate more realistically the capacity of the welded connection. In order to do that, yeah, this is also a graph showing a correlation between the experimental test and those calculated, the strength calculated by the AISC design formula. And if you look at this, for example, for this case, it's almost 3 times larger than those calculated by AISC formula. Yeah. So in order to come up with a more realistic design formula, we needed to have more specimens. So a finite element simulation were run, and in the finite element model, actually we try to kind of simulate the fracture in the weld as well. This is a schematic view of a finite element model, and then the finite element output was validated against the experimental test, and then the finite element procedure. So make sure that it predicts the fracture initiation and also the strength of the connection accurately. So these are the comparison between the experiment, load versus displacement, based on the experimental test, and also finite element output. And these cross mark are where the fracture actually happens in the weld. So a good comparison were observed. And also the validation was also done based on the output of the strain gauge as well. So, and so these are those comparison, and good correlation actually were observed. So, and also the finite element was able to, the finite element solution was able to predict the crack initiation as well. So these elements, these red elements, means that the fracture actually happens in this portion, these elements, so they don't carry load anymore. And then again, the capacity of all parametric study, and also a parametric study was done, 61 specimens, connection, HSS connection specimens were created in finite element model. Again, a correlation were done between the capacity of those specimens calculated by finite element against the capacity of the connection calculated by current formula in AISC. And then, so we try to kind of figure out a new design recommendation. In order to do that, first of all, we needed to know the effective width of each element, because that's a critical point which governs the design of that semi-rigid connection. So I used like a very simple design principle from like all we know from our undergrad courses, which is based on the plane remain plane assumption. So the key is that actually, because the connection is under bending moment, so it makes sense that if we have like neutral axis here, then part of the connection which is under compression stresses. So in that part, actually, both branch wall and also weld thickness participate in transferring the load. This is not something that is being considered in the current design formula in AISC. So they just consider the weld. They don't consider these portion, which is the chord actually contributing in transferring the load. So the equations of compatibility and equilibrium were done over the section. For the moment, this is the compatibility equation, and these two comes from the equilibrium. This is the equilibrium of the forces, and this is the equilibrium of the moment. So I set these moment actually to all moments calculated based on finite element procedure. So these are three unknowns that were meant to be identified by solving these three equations. So I ran these three equations over all 61 finite element solution, and by doing that, be actually effective and also the neutral axis location were calculated. So it was actually for the neutral axis, it was calculated that the location of the neutral axis actually for almost for most of the finite element specimens happened at the 3/4 ratio of the branch depth, which this was also supported by finite element solution as well. And if you see, these blue contours are compression force, and these are the tension force. These green actually contours represent the tension force, and this is the location of the neutral axis, which matches what was calculated based on those three equations. So again, B effective, actually a normalized value of the B effective was represented based on the chord wall slenderness, and these are what were obtained based on the finite element, and these are based on the AISC formula. So, and then it was found that so as you see, these B effective are quite larger. The one calculated based on finite element was quite larger than those calculated by code. So, and another factor that was considered in developing the design recommendation was based on a study was done by Kyle Tusing-Nant and Professor Packer, and they found that actually the weld strength in branch in fillet weld is not actually 0.6 FEX, and it is actually larger. So they proposed this formula. This formula was also implemented in our design formula. So I mean, in our design, we also used the weld strength to be this value. And so these are the proposed design method that this is the neutral axis location. And then according to this, the section modulus could be calculated. So then the correlation based on the new actually design formula, a correlation were done, and also a reliability analysis was done to come up with this phi W as well. So a correlation was done, and as you see, as you compare this graph with the one, the first graph actually is the one with the current provisions of AISC, and the second one is based on the new design recommendation, and so it is observed that they can actually calculate the design, the capacity of the connection more realistically. So and in the another, because it was tried to make it more simple. So rather than the formula proposed by Kyle Tusing-Nant, actually it was assumed that FNW, which is the weld strength, be equal to 1.3 of the in this one, I think. In this one, it'd be 1.3 times of the current value proposed by AISC. So this is a more like simple. It is more simpler, and also it gives also more like good result as well. So, and these are the design recommendations that were proposed. That so basically, if we consider the moment strength could be is can be calculated by multiplying the weld strength and section modulus. So the section modulus can be calculated by this formula, and then the weld strength can be considered 1.3 times of the current value for the fillet weld strength in the code. And so actually this is the end of the study, which was done on the connection design of the like HSS moment connection, and they were quite more like complicated because they are not fully rigid connection. They are semi-rigid. So to find that effective width, so it needs actually more like calculation. But for like fully rigid connection, so actually implementing such a design concept, considering that bearing effect is more it is much simpler, I would say. So here I want to extend this design concept to design of like typical moment connections, those like fully rigid moment connection that we'll deal with, and you will see how that actually implementing that bearing effect would actually help us to get more capacity out of the connection. So this is an example that I did for for a moment connection, and this is like an I-beam, or let's say I-column, connected to a like very thick base plate. So, and these are the geometrical properties of the I or W section. So we can assume that that could be the neutral axis location. So below the neutral axis, both welds and also the W-shaped profile would participate in the transferring the load. And in the tension part, it is only the weld that participate in transferring the load. So, so if we actually use like a conventional method, so how we approach, we just calculate the section properties of the weld. We don't even look at the okay. We also have the I-shaped profile, W-shaped profile. We only calculate the section properties of the weld, and this is how we calculate the welded connection capacity. But if we want to take that bearing effect into our formulation, so we basically can count on this portion of the weld, the W shape in compression portion as well. So in running the formula, actually, so we kind of can count on the compression of that portion of the W shape as well. So we basically need to run the equation of the equilibrium and compatibility. This can be simply done in MathCAD. So all engineers actually use MathCAD to run the calculation, and then we can find the location of the neutral axis and then the compression strength. And then when we find the location of the neutral axis, then we can calculate the capacity of the welded connection. And then in the formula, we can count on the that compression portion of the W shape as well. So if you compare this, see, using this method, we will have the compression, the connection capacity would be 651 kilonewton meter. And if we don't use this, using the conventional method, the connection capacity would be 438 kilonewton meter. So even we can further extend this concept in design of bolted connection as well. So let's say that we have like such a flange connection, like I use a very like simple connection to illustrate this effect. So it is like a very simple flange connection, and with the 4 bolts, and then we can say, okay, that would be the location of the neutral axis. If we use the traditional method, so this is how we actually calculate the capacity of that bolted connection in the conventional method. So we just rely on the capacity of the bolt. And so we calculate the strength in the bolt, the tension in the bolt, and then we calculate moment by multiplying the number of the bolts and the moment arm, I mean the bolt distance. So this is how we normally calculate the flange connection, the bolted flange connection. But if we use that concept and we take like benefit from that compression part of the flange, so we just need to run this equation. This also can be simply done in MATLAB, and to find the location of the neutral axis. And then when we find the location of the neutral axis, we can calculate the moment capacity of the flange connection. You can do such comparison here as well. So this is the moment capacity that we can get by using the bearing effect. It's almost 600 kilonewton meter. And if we go with just conventional method, it is like 494 kilonewton meter. So yeah, that brings these 2 examples actually brings me to the end of my presentation here. I would like to thank Dr. Minsoon from University of Victoria and Dr. Kyle Tussingnant and from Dalhousie University and Professor Jeffrey Packer that actually reviewed this work and also helped to come up and also simplifying the design recommendations. And also I would like to thank Dr. Imanpour from University of Alberta that helped me to and my presentation and also the selection of the subject of my presentation. Also, I also would like to thank from our sponsors of Verendeel Center, and I'm here to answer should you have any questions.